Hello, myself Dr. Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss the problems that are related on the data representation. So generally the data representation is used to represent the numeric data, the character data. The numeric data can be represented by using the various number systems like the binary number system, octal number system, hexadecimal and decimal number system. So here based on how these number system can be converted from one number system to another system and how the character data can be represented by using ASCII code, and the special characters can also be represented with ASCII and BCD. Yeah, and what are the various problem statement related to this data representation can be discussed in this video. The first problem statement is convert the following binary numbers to decimal number system. So here the binary number system can have a base value of 2 and decimal number system is having a base value of 10. So here the first number 101110 and 110101, second number 110 is the third number. So these binary numbers can be converted into the decimal number. To convert the binary numbers into the particular decimal number, the digit multiplied by base value of that particular number system can be used. So here consider the first number, that is the 10110. So here each digit can be considered and which has to be multiplied with the positional value of that particular number system. That is 0 into 2 power 1 plus 1 into 2 power 2 plus 1 into 2 power 3 plus 1 into 2 power 4 plus 0 into 2 power 5 plus 1 into 2 power 6. So these values has to be considered here, and what is the product value that can be obtained can be added so that the number can be converted into the decimal number system. And next consider the second number, that is 110101. Here also 1 into 2 power 0, like that each digit with the positional value has to be multiplied so that the product terms can be added in order to get the actual decimal number. So here 117 is the decimal equivalent of this binary number. Next, the third binary number can be converted in the similar way, and which is the equivalent of 436 in the decimal form. Next, convert the following numbers with the indicated basis to the decimal. So now in the previous problem we have discussed that how the binary number can be converted into decimal. In those cases the conversion methodology can be considering the each digit and multiplying with the positional value of that concerned number system, and those product terms can be summated in order to get the decimal equivalent. So here also it is the base value of 3 number system. So the positional value, each digit has to be multiplied with the positional value. And the second problem is 4310, the number can be represented in the base number system 5. And 50 with the base number system 7. 198 with the base number system 12. How these numbers can be converted into decimal? So here we have to use the methodology that 121 to 1 with a base value 3. So each digit must be considered, that is 1 into 3 power 0 plus 2 into 3 square plus 1 into 3 cube plus 2 into 3 power 4 plus 1 into 3 power 5. So here we have to use this methodology, and the product term can be added here in order to get the actual decimal equivalent. 151 is the equivalent of 121 represented in the base 3 number system. Similar way here with the base 5 number system, we have to use similar means 0 into 5 power 1 and the 1 into 5 square and 3 into 5 square and here 4 into 5 cube. Like that we have to use and convert the product terms. 500 plus 75 plus 5 is 580, which is the decimal equivalent of the number that is represented with a base value of 5. Next 50, that is the number that can be represented with the base value of 7. So here 0 into 7 power 0 plus 5 into 7 power 1. So here this value 0, this is 35. So here the decimal equivalent can be the 35. And 198 can be represented in the base value of 12 number system. So here 8 into 12 power 0. Next 9 into 12 power 1 plus 1 into 12 square. So the product can be the 144 plus 108 plus 8. So here 260 is the decimal equivalent of 198 represented in the 12 number system. So here if at all any number system number can be converted into the decimal number, each digit must be considered and that digit can be multiplied with the place value of the digit and the product term can be submitted in order to get the decimal equivalent of the corresponding number. Next, convert the following decimal numbers to binary, that is 1231, 673, 1998. So here we have to follow the continuous division method in order to get and write the reminders in a bottom-up fashion to get the binary equivalent. So the binary number system can have the base value 2, and by considering the concerned number and divide that number with the 2 and writing the reminders in a bottom-up fashion in order to get the binary equivalent. So here this is 1231. We have to divide with the 2 value. Okay, and here after dividing this, whatever the reminders that can be written in the bottom up fashion. So here we have to divide 1231 with the 2 value. It should be the 650 with a remainder 1. Next again we have to further divide the number with the 2. So that is, so here 307 with 1 as the remainder. Next again further divide this 153. Again further divide this. Again further divide it. So we have to write in a bottom-up fashion all these reminders in order to get the binary equivalent. which can be the value this. So similar way you have to follow for the second number. That is 673 has to be divided with a base value of 2 and this continuous division method can carry out until the number cannot be further divided into, and what are the reminders that are getting can has to be written in bottom up fashion in order to get the binary equivalent. So here the 673 binary equivalent is 10101 4 zeros 1, and for 1998 the binary equivalent is 5100310. So in this way, by using the division method, the binary equivalent can be found. Next problem statement. Convert the following decimals to the bases indicated. So here the number can be 75622 to octal number system. So in order to convert the decimal number into binary, the base value of that particular binary number system is 2. So the number can be divided with the 2. But here the problem can be given, the number has to convert it into octal. For octal number system, the radix or base can be the 8. So this number can be divided into 8 and whatever in a continuous division method, and the remainders can be written in a bottom up fashion. And the second problem 1938, and here this number can be converted into hexadecimal. So with the base value of 16, the number can be divided. And in the third case 175 to binary, with a base value of 2, the number can be divided. So here is the solution. So here 7562 have to divide it and converted into 8. And 1938 we are converted and 792 is in the hexadecimal form. 175 is 1010 and 4 ones in the hexadecimal form. So decimal number, if you want to convert it into particular number system with this base value, the number can be divided continuously and the remainders can be written in bottom up fashion. Next, convert the hexadecimal number F3A7C2 to binary and octal. So here the hexadecimal number is the F3A7C2. So we have to write the binary equivalent of each digit. So 4-bit binary equivalent of each digit can be represented. In order to get the binary equivalent of this hexadecimal number. So the 2 can be represented in the hexadecimal form with a 4-bit binary digit of 0010. C must be represented with 1100. 7 is represented with 0111. And A is represented with 1010. And 3 is represented with 0011. F is represented with 4 ones. So in this way, if you want for each digit, the 4-bit binary equivalent can be written. That series can be the binary equivalent of that particular hexadecimal number. So what is the binary number you can get? That has to be segregated with the 3-bit binary values. Then for each 3-bit, what is the exact decimal notation can has to be written in order to get the octal value. So for this it should be the 2, and for 3 zeros 0 and 3 ones 7. Next 011 it should be 3 and 0102 and 3 ones 7, 1004, 111 7. So this is the octal equivalent of this binary number. So if at all any hexadecimal number is given, In order to convert that hexadecimal into the binary form, 4-bit binary equivalent of each digit can be written. And from that binary equivalent, we have to consider 3-bit binary group and write the decimal equivalent of that 3-bit in order to get the octal equivalent from that binary number. Next, show the value of all bits of a 12-bit register that hold number equivalent to 215 in the decimal form. And this binary can be represented, binary coded octal can be represented, binary coded hexadecimal can be represented, binary coded decimal form, the register value can be represented. So 215. So first we have to find the binary equivalent of 215 by dividing the 215 with the 2 and writing the remainders in the bottom up fashion. So 215 binary equivalent can be 110, 10, 111. And that is in the case of binary. In the case of binary coded octal, the 3 bits can be grouped. So from this binary number, the 3 bits can be grouped. So here the 3-bit group, 3 ones can be equivalent to 7, 0, 1, 0 is equivalent to 2, and the remaining bits we have to represent with the zeros. So it is a 0, 1, 1, 3, 000 is 0. So here the register is a 12-bit register. In order to equate with the 12 bits this value, the preceded zeros has to be added to this number. After adding this, grouping the 3 bits as a group, as a single group, and convert the decimal equivalent of that binary number which is represented in the binary coded octal. So 0327 is in the binary coded octal form. And in case of binary coded hexadecimal form, in the case of binary coded hexadecimal form, the binary number has to be grouped in as a 4-bit. So here the number can be 11010111, and we have to represent this with a 12-bit binary number. So here this is 0, 1, 2, 3, 4, 5, 6, 7 bit. So we have to add the preceded values, the 4 zeros. So this is the binary number, and we have to group exactly the 4 bits. So here 0, 1, 1, the equivalent can be the 7. And in the second group, 1101 is the equivalent value is D. For 4 zeros, the value is 0, which is equivalent to binary coded hexadecimal. So the binary coded hexadecimal of the 215 is 0D7. And binary coded decimal form means for each digit we have to produce the exact binary 4-bit binary equivalent number. So to represent the 5, the 4-bit binary equivalent is 0101, and to represent the 1, 0001, to represent the 2, 0010. So this is the binary coded decimal notation of the number 215. Next, show the bit configuration of 24-bit register when its content represent the decimal equivalent of 295. So this 295 can be represented in a binary form, that is the first question, and the second question is in BCD form. So 295, the binary equivalent can be this, but the register is of capacity of 24-bit. So to represent the 24-bit, for this binary value, the leading zeros can be added. So this is the representation in the binary form. And the next question is, we have to represent that in a BCD. In a BCD form, each digit 4-bit decimal equivalent, binary equivalent can be written. To represent the 5, the 4-bit binary code is 0101. And to represent the 9, 1001. To represent 2, 0010. Remaining all zeros are the leading zeros in order to represent 24-bit register. So in this way, the BCD and binary coded binary form has to be represented for the number 295. Next, decode the following ASCII code. So here the binary code can be given. What is the ASCII code for this? So for each 8-bit code, here a specific letter has to be assigned in the ASCII code. In the ASCII code is American Standard Code for Information Interchange. 255 characters can be represented. So each combination can have a specific meaning, and the letter J value can be equivalent to 10101010. Like that, the next byte can have the value of O, and the next byte can have the value of H, N. So the binary that ASCII code that is represented can be decoded as John Doe. Next, obtain the 9th complement of the following 8-digit decimal numbers. So for these numbers, have to identify the 9th complement. How to get 9th complement means, for this digit, how much amount of what number can be added in order to represent the maximum value of 9. So here consider the first number, that is the 1, 2, 3, 4, 9, 8, 7, 6. So the 9th complement can be, for 6 we have to add 3 in order to get the value 9. For 7, add 2 in order to get the value 9. For 8, 1. For 9, 0. For 5, 4, 5. For 3, it could be 6. For 2, it could be 7. For 1, it could be 8. So the 9th complement of first number can be this. And the second number can also be represented in the similar way, 009801000. In order to get the 9th complement, 99891099. So this is the 9th complement of second number. Okay. So similar way, the third one and the fourth one can be represented. Next, obtain the ones and twos complement of the following 8-digit binary numbers. So the ones complement can be obtained. The ones complement can be obtained by interchanging the 1 as 0, 0 as 1. And the twos complement can be obtained by adding a 1 value to the ones complement. So here the number that is given in the problem is this, and the ones complement of this number is 01010001. This is the ones complement. For this, if you add 1, then you can get the twos complement. So this is the twos complement of the given number. And similar way, the second number is 1601. In order to get the ones complement, 0, 1, 0. This is the ones complement by interchanging 0 as 1 and 1 as 0. And for this ones complement, if you add a 1, then you can get the twos complement. So this is the twos complement of second number. Similar way, all these numbers can be founded the ones complement as well as the twos complement. So for the third number, 0, This is the ones complement, and we have to add a 1 to it. So at last we can get the 1. And for this number, and all are remaining 1. And adding a 1 here, all bits can be the 1 bits. So this is the next number. And for this, if you find the ones complement, all bits are 1s. And if you add a 1 to it, you can get the 2's complement value. So all can be the zeros. At last we can get the 1. So in this way, the 1's complement and 2's complement can be carried out. Next, perform the subtraction with the following unsigned decimal numbers by taking 10's complement of the subtrahend. So the first bit is 5250 minus 1321. And second bit is 1753 minus 8640. Third bit is 20 minus 100. Fourth bit is 1200 minus 250. So this is the first number, and the second number is the decimal equivalent can be carried out. And here the 2's complement of subtrahend can be taken. With the 2's complement addition, the subtraction can be carried out. So here the first number and the 2's complement of second number can be taken. And by adding it, if at all extra carry is produced, that carry can be discarded. And here, after adding, in the first case, the extra carry produced, that is discarded. In the second case also, after addition of 2's complement of subtrahend, extra carry can be produced, that is discarded. But in the case of third one, no extra carry can be produced. So the 2's complement of this result, this number, the sum addition, whatever obtained is the result. So hence the number can be the negative number. In the fourth case, the extra carry that is produced can be discarded. Perform the arithmetic operations plus 42 plus minus 13 and minus 42 minus 13 in binary using signed 2's complement representation for negative numbers. So plus 42 can be representation of this, minus 42 can be represented with a signed bit of 1. Plus 13 of binary equivalent is this, minus 13 can be with a signed bit of 1. So the first problem is plus 42 minus 13. So 42 value binary digit and minus 13 value can be considered and added. And in case of minus 42 plus 13. So here minus 42 value and plus 13 value and performing the addition. So with the 2's complement addition, the subtraction can be carried out. Next, perform the following arithmetic operations with the decimal numbers using signed tens complement representation for negative numbers. So here on the decimal numbers, we are using the tens complement addition, thereby performing the subtraction. So the first bit is minus 638 plus 785. The second bit is minus 638 minus plus 185. So here 638 plus 785. So here we have to perform following arithmetic operation with decimal numbers using signed tens complement form. So here the negative number has to be represented in the tens complement form. First find the nines complement, add a 1 to it in order to get the tens complement of 638. For that, the negative number can be represented in the tens complement that can be added, so that we can get the result of 147. And here both are negative numbers, so both numbers can be represented in the tens complement form. First, we have to find the nines complement, and for that nines complement, want to add the 1 in order to get the tens complement and perform the addition. So, minus 638 minus 185, we can get that minus 823. So, here the result can be in the tens complement form. Next problem statement, perform the arithmetic operations plus 70 plus 80 and minus 70 plus minus 80 with binary numbers in the signed 2's complement representation. Use 8 bits to accommodate each number together with its sign. Show that overflow occurs in both cases, that the last two carries are unequal and that they are in a sign reversal form. So here plus 70 plus 80, the number has to be represented. And here minus 70 and minus 80. So here if you consider the sign bit, here it is a plus 1. 1 means in the sign bit it is a negative number. So the negative number means which indicates the positive number before that can be converted into negative number, so overflow can be occurred. So in case of this, the two negative numbers can be generated a positive number. Next, a 32-bit floating point binary number has 8 bits plus sign for the exponent and 26 bits plus sign for the mantissa. The mantissa is a normalized fraction. Numbers in the mantissa and exponent are in signed magnitude representation. What are the largest and smallest positive quantities that can be represented excluding 0? So the mantissa has to be represented with 26 bits and exponent can be represented with 8 bits. So total 1 bit for the sign bit, total 36 bits can be represented. So the largest can be the 1 minus 2 power minus 26. And with the normalization, it can be represented with 0.100 with the 25 bits. So in this way, the floating point number has to be represented plus or minus the sign bit. Next, the mantissa multiplied by the radix power exponent form. Represent the number plus 46.5 as a floating point binary number with 24 bits. The normalized fraction mantissa has 16 bits and the exponent has 8 bits. So this is the 46 value in the binary, and one is to represent the 0.5 after the decimal point. This is the binary representation. So 24-bit mantissa has to be represented by placing the extra zeros, and 8-bit is used to represent the exponent. Next question, what is the value of the output H in figure 1 if input A is 1001? S is equal to 1, IR is equal to 1, IL is equal to 0. This is the shifting circuit. So, if it all the selection input is 1 and IR is equal to 1, IL 0. That is IR is equal to 1 means it is a right shifting. So, the values that has to be shifted, and after IL become the 0. So it has to perform S is equal to 1 and the IR value has to be 1 and IL is equal to 0. So the shift operation has to be performed on this number. The A value can be the 1001. So 1001 has to be shifted left. What is the wrong with the following register transfer 3 statements? The first statement xt colon AR complement can be transmitted to AR when AR is equal to 0. Next, YT R2 content can be transmitted to R1 and R3 content can be transmitted to R1. In case of third one, ZT, AR content is transferred to PC. PC incremented value can be transmitted to again PC. So they cannot complement and increment the same register at the same time. So here AR complement can be used and can be transmitted to the same register. So this cannot be performed the same register to parallel operations. The second one cannot transfer two different values R2 and R3 to the same register, the R1 at the same time. The third one is also incrementing the PC value, updating at the PC at the same time. So these three statements can give a conflict of operation. So these are the problems that are related to the data representation during the number system and ASCII representation. And these problems are taken from the reference textbook of Computer System Architecture by Maurice Mano. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.